So in this video, we're going to be talking about why the periodic trends are the way that they are. So we introduced 4 different trends in the previous lesson, and thankfully, they're all explained by the same phenomenon. So they can essentially all be explained in terms of the strength of attraction between the nucleus and the valence electrons. So we know that the nucleus contains protons, which are positively charged, electrons are negatively charged, and opposite charges are attracted to one another. So the nucleus and the electrons are attracted to one another. All of the trends that we are looking at are specifically dealing with the valence electrons. For radius is essentially the distance between the nucleus and the valence electrons. Ionization energy and electron affinity are adding or removing a valence electron, and then electronegativity deals with bonding, which also involves our valence electrons. So all of these trends are really dealing with or coming from trends in strength of attraction between the nucleus and the valence electrons. And this is dictated by what is known as Coulombs Law. Which tells us that the strength of the attraction is equal to the product of the charges over the square of the distance between them. So Coulomb's law shows up all over the place in chemistry as sort of a qualitative justification for things. So we're never going to use Coulomb's law quantitatively. I'm never going to ask you to do calculations using this equation. But it is the basis for a lot of why things happen the way they do in chemistry. So E stands for energy. It is the force of the attraction between particles. This does also apply to repulsions as well, but we're using it for the attraction side of things here. Q represents charge, so Q1 and Q2 are the charges on charged particles. For us, that is the nucleus and the valence electrons are sort of the particles that we're thinking about here. And then R is the distance between charged particles. Again, where our particles that we're thinking about are the nucleus and the valence electrons. So Coulomb's law applies to any and all interactions between charged particles of any kind. So it can be applied to a lot of different scenarios to help explain things in chemistry. So for us, we're looking at the nucleus as sort of being a single particle, even though we know it's comprised of a bunch of subatomic particles, and then our valence electrons are the things that we are thinking about. So the takeaway from Coulomb's law is that the energy or the strength of the attraction is related to 2 main things: the size of the charge and the distance between those charges. And the way that it's related, we can see from this equation, which is the only reason why I show you this equation, is to get that larger charges lead to stronger attractions. Since the charges are in the numerator of this expression, as these values get larger, as the magnitude of the charge gets larger, this value is going to get larger as well. And since this is in the denominator, the opposite is going to be true. The closer charged particles are to one another, the stronger the attraction. So closer together means that this value would be smaller. As our denominator gets smaller, the value of E is going to get larger. So as your particles are being held closer together, they're going to be more strongly attracted to one another. So these are the ideas that are really behind all of those periodic trends, is how these ideas of the size of the charge and the distance between the charges actually play out in atomic structure. So we talked in the previous video about how the various trends change moving down a family and how they change moving across a period. And there are essentially two different explanations depending on which direction you're moving, whether you're moving vertically or horizontally across the periodic table. So when you are moving up or down a family within the periodic table, or when you're comparing, the main difference in terms of atomic structure that is giving rise to these trends is this distance idea. So the farther down a family you go means that the valence electrons are in a higher energy shell. Which is farther away from the nucleus. So we've talked about how the different shells of electrons, as you get higher in energy, you're getting farther and farther away from the nucleus. So the n equals 1 is pretty darn close to the nucleus. As you get out to higher energy shells, we have a greater distance between the nucleus and the valence electrons. Oh hey, distance was one of our factors that affected the strength of the attraction. So when your valence electrons are farther away, essentially the nucleus and the valence electrons can't feel each other as much, so they're not as strongly attracted. So this is what's giving rise to all of those vertical trends that we talked about. Larger radius kind of is self-explanatory, I guess, from what we've talked about thus far. Electrons are farther from the nucleus in higher energy shells. Gives us a larger radius. If there is a weaker attraction, that means electrons are going to be easier to remove, which gives us that lower ionization energy that we talked about. If the nucleus is not very attracted to the electrons it already has, it's not going to be very attracted to any additional ones that you may add. Meaning it doesn't have a very high affinity for electrons, so it's going to have a lower electron affinity. And again, if it's not very strongly attracted to the electrons it already has, it's not going to be strongly attracted to any electrons that may be available via bonding. which leads us to the low electronegativity that we see near the bottom of the periodic table. So all four of these trends are really coming from this same idea that as you move down a family, you're adding shells of electrons, which makes the nucleus and the valence farther away and therefore not as strongly attracted to one another. When you're comparing across a row, across a period, we have a different justification. The valence shell, as you move across a period, is staying the same. So as you're moving left to right, you're adding electrons pretty much to the same shell. So you're not getting that sort of big jump that we do going down a family, but what is changing is the number of protons in the nucleus, which is giving us a larger charge on the nucleus. So as we move left to right across a period, we're increasing the atomic number, we're increasing the number of protons, we're increasing the charge on our nucleus, which leads to a stronger attraction to the electrons. So as you're moving left to right, across a period, atomic number increases, which means the charge on the nucleus is increasing. Which leads to a stronger attraction to all of the electrons in the atom, actually, but the ones we're interested in are the valence electrons. And this stronger attraction is what's giving rise to the left to right trends across the table. So since the valence electrons are more strongly attracted to the nucleus, they actually get pulled in a little bit closer, which is why our atoms actually get smaller in radius as we move left to right. They're more strongly attracted to the nucleus, so they're going to get harder to remove. Which matches our trend of higher ionization energy as we move left to right. Electrons are going to get easier to add. The more attracted an atom is to the electrons, the valence electrons it already has, the easier it's going to be to add more. Attractive forces are always stabilizing. So as we move left to right, we generally get higher electron affinity. And similarly, if there's a stronger attraction to the valence electrons that an atom has by itself, there's also going to be a stronger attraction to valence electrons that are involved in bonds. So electrons in bonds more attracted to nucleus, which gives rise to the higher electronegativity that we see as we move left to right. So all of the trends that we talked about are based in these two ideas. And the only difference is whether you're comparing two elements in the same family or two elements in the same period, for which of these justifications is more applicable. But it all comes back to the atomic structure, how the orbitals, how the electrons are arranged in relationship to the nucleus, that gives us all of these different features that we can predict just based on the way things are organized on the periodic table.